Hello everyone. Welcome to Chapter 35, Display Systems and Electronic Images. The first thing I'd like to say is be sure to read the chapter and do the workbook questions. I've created a practice quiz for you to do. I think it's 30 questions. This is actually a relatively short chapter, so it shouldn't take you too long to get through it, and it's a lot of just terms and definitions. So the first thing we're going to talk about is a liquid crystal display, otherwise known as an LCD monitor. And this is basically the monitor type that we use in radiology. So with the advantages, it's lightweight, it's portable, fairly inexpensive, a wide range of sizes. Obviously it's flat shape, so it takes up less space. It doesn't really produce any heat, and there is little reflection of light from the room. The main disadvantage, and we'll cover this again in a minute, but the main disadvantage is that it has to be viewed straight on. So if you're standing at an angle, you really do not have a good viewing of the image. So how does an LCD work? It basically works similar to polarized sunglasses because it reduces the reflective light glare. But basically what I want you to do is watch the videos. I've selected several videos that talk about polarizing light and how an LCD monitor is constructed, and they do a very nice job at explaining that, much better than I could. So please watch those videos and read the chapter, and I think you'll have a pretty good grasp. This next slide just shows basically the construction, and what you need to know is just the simple construction. It's two glass plates. There is a liquid crystal that's placed in between. That's why it's called a liquid crystal display. And that it has a polarizing filter that helps filter the light. There are two different types of LCD monitors that are used. One is a passive matrix and the other is an active matrix. In radiology, we use the active matrix, but if you use a watch or a calculator, that's using a passive matrix. And what that really means is it's useful in small screens, and it has a reflective filter that reflects the light. So the mirror reflects the room lighting or sun lighting for the entire screen. It has a slow response time and poor contrast, which is why we do not use it in radiology. What we use in radiology is an active matrix, and this is needed for the high resolution images. And what makes this so special is that each pixel has this thin film transistor, which is basically the electronics attached to each pixel, so that that's going to be able to read the information. And so this gives you a fast response time with no flicker, and it allows the electrical signal for each subpixel to be read. And then there's a backlighting that's applied, which we'll get into. Again, here's the two different types of LCD, the passive matrix and the active matrix. And what you really notice is that with the active matrix is it's a little bit more complex, and it has the thin film transistors attached to it. What is a dead pixel? And so the book talks a little bit about that. So resolution is stated in the number of hardware pixels on the entire screen. So for an LCD screen, the pixels are actually embedded in the screen itself. So if you poke the screen, like it says here, if you're poking the screen, you can actually cause damage, which is a dark pixel like this one. So this one up here that has the black pixel in it is caused by someone poking the screen. And it remains dark because it's constantly receiving a signal. If you have a truly dead pixel, it will actually show up white, like here. And then again, we talk a little bit about how resolution is measured, and it's measured in megapixels, which should sound familiar. So in flat panel display, the lighting that you receive is either emissive display or non-emissive display. So for the liquid crystal display, or LCD, it's a non-emissive display because you have to have an optical effect to convert the sunlight or light from some other source. If you have an emissive display, as in plasma screens, it converts the electrical energy into light. Again, this is just another slide that's showing the difference between emissive and non-emissive. What I want you to know is that an LCD is a non-emissive display, and plasma or old cathode ray tubes are emissive display. That's all I really want you to know about it right now. Again, this last slide here is just talking about, or that's next to the last slide, is just showing you the difference between an LCD monitor, an OLED, so this would be an LED monitor, and plasma. And it's really showing you the pros and the cons to each of them, and why we end up using an LCD as opposed to some of these others. The LED is actually up and coming, but plasma will probably not be used in radiology for a while just because it's too expensive. Again, some of the advantages and disadvantages, I put this on here. The biggest disadvantage to an LCD is that it has a limited off-angle viewing. The other things is it doesn't show true black. It's also temperature dependence, and it has a warm-up time. So you have to actually warm this up for about 10 to 15 minutes in order for the radiologist to start diagnosing. So that actually, it has a slow warm-up. And then some of the image retention can cause ghosting, which is not good when you're trying to diagnose image. Nature of pixels into the display. So this slide is talking about when you're talking about an LCD, you can either have a color screen or a black and white screen, which is a monochrome. So we use a monochrome. And when we start talking about 3 subpixels, red, yellow, blue, or a triad make up the pixels in a color monitor, we don't need color in the monochrome. So each single subpixel actually covers 3 times the area. So that is a huge advantage. So this boosts the image resolution because you can have smaller pixel units. So this picture basically over here shows what I'm talking about. Is in this color, you really are having a hard time picking out the black V in here, but because this has 3 times the pixel resolution, you actually can see the V really well in the monochrome monitor. And we don't really need color in radiology. Spatial resolution of a display monitor is measured in megapixels, is what I mentioned. So 3 to 5 megapixels is considered high quality. For mammography, we need to use 5 to 7 megapixel monitors because you're talking about tiny specks that you're looking at. So a class 1 display monitor is what's used by the radiologist to diagnose the images. Class 2 display monitors are what we use in the x-ray rooms, and those are not considered diagnostic quality, and they usually are 1 to 2 megapixel quality. And then the main thing you need to remember is that the display monitor is considered the weakest link in the entire imaging chain. The detector is actually the strongest link, and the display monitor is the weakest. And here, this is the last slide, and this is just giving you an example that you can see 2 megapixel, 5 megapixel, and 8 megapixel. So as the megapixel goes up, obviously the detail or sharpness is better. So we're using a 1 to 2 megapixel monitor, where the radiologists are using 5 to 7. So that really gives you an idea of the detail that they have. And that is the lecture.